Biprism experiment. To measure the wavelength of light, an optical bench is used. The optical bench is about 1.5 meters long and scale is marked along its length. 4 adjustable stands carrying the slit S, biprism B, lens L, and the micrometer eyepiece E are mounted on the optical bench as shown over here. The slit and the biprism can be rotated about horizontal axis. Initially, the slit, biprism, and eyepiece are kept at the same height such that their centers are in same line. The slit is made narrow and is illuminated by sodium vapor lamp, that is monochromatic light. The stands carrying the slit and biprism are kept close together. The slit is kept vertical. The biprism is now rotated slowly about a horizontal axis so that its refracting edge becomes parallel to the slit. When the refracting edge of biprism becomes exactly parallel to the slit, the interference pattern consisting of alternate bright and dark bands appears in the field of view of the eyepiece. Now we can measure the wavelength of light using this equation. X is equal to lambda d upon small d, or lambda is equal to x into small d upon d. Measurements. 1. The distance between slit and eyepiece D can be easily measured from the scale marked on the optical bench. 2. The bandwidth x is measured with the help of micrometer eyepiece. The vertical crosswire in the eyepiece is adjusted at the center of a bright fringe. The micrometer reading is noted. Now, eyepiece is moved horizontally until the crosswire has moved over a known number n of the bright fringes. Again, micrometer reading is noted. The difference between the two readings of the micrometer gives the distance x through which eyepiece is moved. Then, the average distance between two adjacent bright fringes is given by x is equal to small x upon n. 3. The distance d between two coherent sources cannot be measured directly because the sources are virtual. Hence, we use the conjugate foci method for determination of small d. In this method, object and image distances get interchanged in two adjustments as shown over here. The convex lens of short focal length is introduced between the biprism and the eyepiece. Without disturbing slit and biprism, the eyepiece is moved back so that its distance from the slit becomes greater than 4 times the focal length of the lens. The lens is moved towards the slit and its position L1 is so adjusted that two magnified images A1 and B1 of S1 and S2 are formed in the focal plane of the eyepiece. The distance small d1 between A1 and B1 is measured by the micrometer. Then, referring to this figure, we can write size of image upon size of object is equal to distance of image upon distance of object. Therefore, small d1 upon small d is equal to v upon u. The lens is now moved towards eyepiece to the position L2, where two diminished images A2 and B2 of S1 and S2 are formed in the focal plane of eyepiece. The distance small d2 between A2 and B2 is measured by the micrometer. Then by the principle of conjugate foci, we can write small d2 upon d is equal to u upon v. Taking the product of equations small d1 small d2 upon small d square is equal to v upon u into u upon v, that equals to 1. Therefore, small d square is equal to small d1 into small d2, or small d is equal to square root of small d1 into small d2. Thus, knowing d, x and small d, we can calculate the wavelength lambda of monochromatic light by using the equation lambda is equal to x into small d upon d.